LLMs are trained on the vastness of the internet, but they don't naturally know how to be helpful or safe. To bridge this gap, we use RLHF, reinforcement learning from human feedback. This is the alignment problem, ensuring that the model's goals and behaviors match human intentions and ethical standards. RLHF is the primary tool used to solve it. It starts with supervised fine-tuning, or SFT. Experts provide demonstrations of how the model should respond to various prompts, giving it a baseline persona. But imitation only goes so far. To truly excel, the model needs to understand preferences, which response is better and why. This leads to the second stage. In stage 2, we train a reward model. Humans are shown several responses to the same prompt and rank them. This data is used to teach a separate model how to score outputs. This reward model becomes a mathematical representation of human preference, capable of assigning a score to any output based on its quality and safety. Now comes the final stage, the reinforcement learning loop. The model generates responses, and the reward model provides immediate feedback, steering the model toward higher scoring behavior. Most systems use PPO, an algorithm that makes small, stable updates to the model's policy, ensuring it doesn't deviate too far from its original pre-trained capabilities. To prevent the model from gaming the reward system, we use a KL divergence constraint, which penalizes the model if its behavior changes too drastically from the base model. Through millions of iterations, the model converges on a behavior that is both highly capable and closely aligned with human values. A newer approach called Direct Preference Optimization, or DPO, simplifies this by optimizing the model directly on preference data, eliminating the need for a separate reward model. Alignment techniques like RLHF further refine the model by incorporating human feedback, ensuring the model's outputs are helpful, honest, and harmless. Monitoring the training loss is critical. A smooth descent indicates the model is successfully learning the patterns of the new task. However, we must guard against overfitting, where the model memorizes the training data perfectly but loses the ability to handle new, unseen inputs. In summary, fine-tuning is the process of specializing pre-trained models using efficient methods like LoRa to create task-specific experts. Mastering fine-tuning is the next logical step for any developer looking to move beyond simple prompts and build truly integrated AI systems. Fine-tuning proves that intelligence isn't static, it's a continuous process of learning, adaptation, and specialization. We've tailored our models, but what about new architectures? Join us in the next episode as we explore Mamba and the future of sequence modeling. Follow for more.